Welcome you all for the video lecture on fluid mechanics and machinery. This is the second video of module 1 fluid properties. Myself K. Davaslingam, Assistant Professor Mechanical. In previous video lectures we are deal with overview of fluid mechanics and fluid properties like density, weight density, specific volume and specific gravity. In this video lecture we are going to deal about viscosity. Now we are going to identify which tank will fill faster than other tank. That means which liquid has high restriction to flow. Look at the first tank. It will fill faster than second tank, as well as the first tank liquid has less restriction to flow and second tank liquid has more restriction to flow. So we can say if the fluid has low viscosity, it has more flow. If the fluid has high viscosity, the flow is less. The below figures are showing the difference between non-viscous and viscous fluid. We can take the example of non-viscous as water. For viscous, take it as honey. Look at the figure which describes first tube liquid has high viscosity. That's why the ball is not moving faster. And look at the second one. When compared to first one, it moving faster. That means it has medium viscosity. And look at the third one. The ball moving faster than other two, so it have low viscosity. The second image also shows that the object and viscosity relationship. Look at the third one. We have three containers which has three different liquids, namely honey, oil and water. So honey has medium level of viscosity and this particular oil has high viscosity and water has less viscosity. So we can say these three containers has three different viscosity of fluids. Next we are going to see shear force on fluid. Look at the bottom and top layer of the fluid flow. Look at the bottom layer. At here this viscosity is low. At top layer the viscosity is high. Technically we say bottom layer is no slip condition, at top layer is free stream velocity. Look at the second image. At the bottom layer there is high restriction, that means high viscosity, so there is no flow. Shear force means we give the force at the top layer. Look at the figure. Here at the top of the cards we give the force, it will move on. Look at the fourth image. At the bottom there is no velocity, but at the top layer there is high velocity. When the height increases, the velocity also increases. That means at bottom layer there is high viscosity, at top layer there is less viscosity. So shear stress is equal to force divided by area, shear strain is equal to displacement divided by thickness. As we seen earlier, at the bottom of the point there is low velocity, that means high viscosity, and at top layer that is high velocity and low viscosity. In this graph, x-axis denotes u, velocity. Here the y-axis denotes y, that means height. At top layer that is high viscosity, so u plus du. The adjacent layers are reducing the velocity, so this will be reduced gradually. At the bottom the velocity will be 0. This figure clearly describes the velocity variation. Look at the figure. Here the velocity varies linearly or gradually towards the height. So we can say as a statement, the shear stress is proportional to velocity gradient, that is du by dy. As an expression, tau directly proportional to du by dy, where tau equal to shear stress, du by dy is velocity gradient. So this will become as equation tau equal to mu du by dy. So this will become as equation tau equal to mu du by dy. This is a very important equation. From that equation, mu equal to tau du by dy, we can come to another conclusion statement. Viscosity also defined as shear stress tau required to produce unit rate of shear strain, that is tau also proportional to d theta by dt, that is rate of shear strain. We have different types of units. First one is MKS units of viscosity, that is kgf second per meter square, and CGS unit of viscosity, this is dyne second per centimeter square, where kgs is replaced by dyne and meter square is replaced by centimeter square. Here 1 dyne equal to 10 power minus 5 Newton. Next one is SI unit of viscosity. This is what we are using. The unit is Newton second per meter square, that is equal to 1 Pascal second. We simply say it as pas. This is also important. 1 centipoise equal to 1 by 100 poise. This is briefly write as 1 Cp equal to 1 by 100 P. Next one is kinematic viscosity, nu. Kinematic viscosity is obtained by dividing the absolute viscosity by the mass density of the fluid at the same temperature. Here the formula nu equal to mu by rho. The kinematic viscosity unit is meter square per second. Here the unit also important, and where mu equal to viscosity, rho equal to density. Here 1 stoke equal to 10 power minus 4 meter square per second, 1 centistoke equal to 1 by 100 stoke. Here formula of viscosity. Here 6 number of formulas are there, that is very much useful to solve the problems. Here the Newton law of viscosity, we find out tau equal to mu du by dy. This is first equation. Second one is here nu equal to mu by rho. Nu is kinematic viscosity, where mu equal to dynamic viscosity, rho equal to mass density. Here the unit conversion also important. SI unit viscosity is Newton second per meter square, that is equal to 1 pas, or 1 centipoise equal to 1 by 100 poise. Here mu equal to viscosity, rho equal to density. This will be the equation number 2. This is equation number 3, mu equal to pi dn by 60. And equation number 4, shear force equal to shear stress into area, or shear stress equal to force divided by area, and torque T equal to force into d divided by 2. The d is diameter, where power equal to force into velocity is equal to 2 by nt by 60. Next we are going to solve few problems. This is problem 1.3. It contains 1 marks. It was asked in IES 2004. An oil of specific gravity 0.9 has a viscosity of 0.28 stokes at 38 degrees Celsius. What will be its viscosity in Newton second per meter square? Here the specific gravity S equal to 0.9. S is given, and viscosity of 0.28 stokes, that means kinematic viscosity. Stokes they are given, so kinematic viscosity. Here the 38 degrees Celsius is a superimposed data. Here we have to find out what will be the viscosity in Newton second per meter square. So we have to find out dynamic viscosity. They are given 4 options. So first we are going to write the given data. The density of liquid is equal to S into density of water. Here S is given, that is 0.9. So specific gravity is 0.9. Apply this in above equation. 0.9 into 1000, we get density rho equal to 900 kg per meter cube. Then nu equal to 0.28 stokes, that is equal to 0.28 into 10 power minus 4 meter square per second, because 1 stoke equal to 10 power minus 4 meter square per second. Solution: nu equal to mu by rho. So we have to find out dynamic viscosity. So rho we already find out 900 into nu is 0.28 into 10 power minus 4. Finally we find out mu equal to 0.0252 Newton second per meter square. So the answer is C. Next question is 1.4. It contains 1 mark. It was asked in IES 2011. Newton law of viscosity relates. They are given 4 options. At bottom velocity is 0. At top layer the velocity will be maximum. So we know the relationship tau equal to mu du by dy. That is Newton law of viscosity. Tau is shear stress. Mu is dynamic viscosity. Du by dy is velocity gradient. Velocity gradient is also equivalent to rate of shear deformation. That was asked here. Look at the option B. Newton law of viscosity relates to rate of shear deformation and shear stress. So the answer will be B. Question 1.5. It also contains 1 mark. It was asked in IES 2009. What is the unit of dynamic viscosity of a fluid termed poise equivalent? It was direct question. Here we can identify dyne second per centimeter square. This is the CGS unit. So the option is C. Next we are going to see problem 1.6. It contains 8 marks. If the velocity distribution over a plate is given by u equal to 2 by 3 y minus y square, in which u is the velocity in meter per second at a distance y meter above the plate. Determine the shear stress at y equal to 0 and y is 0.15 meter. Take dynamic viscosity of fluid as 8.63 points. In this problem, they are given u velocity as a function 2 by 3 y minus y square. We can also understand that the given function is meter per second, so we can absolutely say that is a velocity. Y is 0 and y is 0.15 meter. That means they are given 2 points. Also take dynamic viscosity mu equal to 8.63. Also they say it as poise, so we can confirmly say that that is dynamic viscosity. Next we are going to write the given data. As we already discussed, u equal to 2 divided by 3 y minus y squared, velocity as a function. Here we can differentiate du by dy equal to 2 by 3 minus 2y. We know the formula tau equal to mu du by dy, where tau equal to shear stress, mu equal to dynamic viscosity, du by dy is velocity gradient. Next we are going to solve this problem. First we apply y equal to 0 and y equal to 0.15 meter, we are applied y equal to 0 in above differentiated equations. So we find out du by dy at y equal to 0 equal to 0.667, and also we apply du by dy at y equal to 0.15. We found 0.367. So the value of mu is given as 8.63 poise. So 1 poise equal to 1 by 10th of Newton second per meter square. So we have to convert the unit poise into SI unit. Will become 0.863 Newton second per meter square. We have to determine the shear stress at each point, that is y equal to 0, y equal to 0.15. First we are going to find out shear stress at y equal to 0. From this equation tau equal to mu du by dy, we are going to apply this y equal to 0. We find out 0.5756 Newton per meter square. Next we are going to find out shear stress at y equal to 0.15. So while applying tau equal to mu du by dy equation, we get 0.3167 Newton per meter squared at the point y equal to 0.15. Next we are going to see problem 1.7. It contains 8 marks. Calculate the dynamic viscosity of an oil which is used for lubrication between the square plates. So they are given size of the plate is 0.8 meter into point and an inclined plane with an angle inclination 30 degree as shown in figure. So this is the angle 30 degree and weight of the square plate is 300 Newton. So this 300 Newton weight is acting on the sliding bar and it slides down the inclined plane with the uniform velocity of 0.3 meter per second. The thickness of the oil film is 1.5 millimeter. Here this layer is inclined at 30 degree. Then this square plate is like to slide down. Here the viscous oil is filled. The distance between the viscous oil is T equal to 1.5 millimeter. The weight W is acting downwards, that is 300 Newton. So here we can say, here we can take two component of forces, horizontal and vertical forces. Here the viscous force is acting this direction, so we have to take this force along this direction. Next we are going to write given data. Here the area of the plate is 0.64 meter square and the angle of plane is theta equal to 30 degree. So the weight is given W equal to 300 Newton. Here the velocity is given U equal to 0.3 meter per second. The thickness of the oil layer dy equal to 1.5 millimeter. So that will be converted into 1.5 into 10 power minus 3 meter. Next we are going to resolve forces as two components. One is W equal to, one is W cos theta, another one is W sin theta. The force is influenced to slide down is W sin theta. So we have to take W sin theta as a influenced force. As we know, tau shear stress equal to force divided by area. Here we have to take the force as W sin theta because it's the influence force to flow down. Now we find out tau equal to force divided by area, that is 150 divided by 0.64 Newton per meter square. We keep as it is 150 divided by 0.64. Here du change of velocity, du equal to u minus 0. U is velocity at given point, 0 is at initial point. At given point u is equal to 0.3 and dy equal to 1.5 into 10 power minus 3 meter. Next we have a well-known formula, tau equal to mu du by dy. Now we apply the shear stress value. Mu we have to find out. Du just now we found out 0.3, dy value 1.5 into 10 power minus 3. From that find out mu equal to 1.17 Newton second per meter square. We also convert the dynamic viscosity value in poise, that will become as 11.7 poise. Next we are going to solve problem 1.8. It also contains 8 marks. The dynamic viscosity of an oil used for lubrication between shaft and sleeve is 8 poise. The shaft of diameter 0.4 meter and rotates at 190 rpm. Calculate the power lost in the bearing for a sleeve length of 90 mm. The thickness of the oil film is 1.5 mm. Here look at the figure. Here the diameter is 0.4 meter and the distance between the shaft and sleeve is 1.5 mm. The length of the sleeve is 90 mm. First we write the given data. Viscosity mu equal to 6 poise, so that we convert 0.6 Newton second per meter square. and the diameter of the shaft is equal to 0.4 meter, and speed of the shaft is n equal to 190 rpm, and sleeve length is L equal to 90 millimeter, that we convert into 90 into 10 power minus 3 meter. The thickness is T equal to 1.5 millimeter, that converted into 1.5 into 10 power minus 3 meter. Next we are going to solve this problem. First we are going to find out tangential velocity u equal to pi dn by 60, where d equal to 0.4 and n equal to 190, that will become the tangential velocity is equal to 3.98 meter per second. Then we know u minus 0. U is given velocity at a point, 0 is initial velocity, so the change in velocity is, just now we find out u equal to 3.98 meter per second. Next, the given data is dy, change of distance, t equal to 1.5 into 10 power minus 3 meter. So well known formula tau equal to mu du by dy. From that we apply the known value and found out tau equal to 1592 Newton per meter square. Next, shear force F equal to shear stress into area. So we apply the known values, where tau equal to 1592 Newton per meter square and shear area is pi dl. Now we apply the value 1592 into pi into 0.4 into 90 into 10 power minus 3, where d is 0.4, L is 90 into 10 power minus 3. So we found out the value F equal to 180.05 Newton. Next we have to find out torque equal to force into diameter divided by 2. So we apply the known value, force equal to 180.05 and diameter is 0.4. So we find out T equal to 36.01 Newton meter. In problem they are asked calculate the power lost. So we have to find out power. So power P equal to F into U, or power equal to 2 by nt by 60. We apply the value, that is n is 190 rpm, torque is 36.01 Newton meter. So finally we find out the power value as 716.48 watts. Next one is viscosity comparison. First comparison is dynamic viscosity with water versus gas. We are well known about mu equal to tau du by dy. Here look at dynamic viscosity value of water equal to 10 power minus 3 pascal, and dynamic viscosity of air, that is equal to 2 into 10 power minus 5 pascal. So we can conclude mu of water is greater than mu of air. That means dynamic viscosity of water is greater than dynamic viscosity of air. Next one is kinematic viscosity with water versus gas. We know the formula nu equal to mu by rho. Here we found out nu of water, that means kinematic viscosity of water is 10 power minus 6. Here the nu of air, that means kinematic viscosity of gas is 1.67 into 10 power minus 5 meter square per second. So we can conclude kinematic viscosity of water is less than kinematic viscosity of air. This is the first set of comparison. These are all the points which will be useful for your competitive exams like GATE, IES. Here we can understand the effect of temperature with dynamic and kinematic viscosity and effect of temperature with liquid and gas. Look at here, while we increase the temperature of the liquid, the dynamic viscosity will decrease, as well as kinematic viscosity also decrease. While we increase the temperature of the gas, the dynamic and kinematic viscosity will increase. So effect of pressure with water versus gas. Here, while we increase the pressure, there is no significant changes in dynamic and kinematic viscosity, only changes in gas. That is, while we increase the pressure, the kinematic viscosity of gas will decrease.
Next one is drinking water. Without the water, we are not able to survive. In technically, we say the water is neutron fluid, standard liquid. The next one is butter. For butter, we need a small force is required to flow as a fluid. We call it as dilating fluid. Butter is the example of dilating fluid. Next one is milk and blood. It is the example of pseudoplastic fluid. Next one is we are using day-to-day life toothpaste. It is a technical name of Bingham plastic fluid. It requires initial force to flow. Next one also we are using day-to-day life cooking oil and honey. In technically we say it as thixotropic fluid. This is also known as thinning fluid. Next one is rheoplastic fluid. Example is cream. It is also called as thickening fluid. This is the comparison between Newtonian and non-Newtonian fluid. The only Newtonian fluid is water. The other fluids are known as non-Newtonian fluid. Look at the top curve. It denotes fluid requires initial shear force. With this shear force, it will flow.
Of Newtonian and non-Newtonian fluid, if we are going to see question 1.9, it contains one more. It was asked in IES 2007. Assertion A. Blood is a Newtonian fluid. The reason: the rate of strain varies non-linearly with shear stress for blood. Already we seen milk and blood are pseudoplastic fluid, but in assertion blood is said as Newtonian fluid. So the assertion A is wrong. Next one is reason: the rate of strain varies non-linearly with shear stress for blood. Look at the figure. Here the pseudoplastic is non-linearly varies. So the reason R is correct. So here is the explanation. Blood is a pseudoplastic fluid and shear stress is given as tau equal to mu du by dy power n, where n less than 1. But for Newtonian fluid, n equal to 1. But pseudoplastic fluid, n greater than 1. Assertion is wrong, reason is correct. In this video, we had seen viscosity.